We're now going to take what we have learned about imaginary numbers and apply it to operations with radicals, multiplication, division, and adding and subtracting. So we already know that if I to the 0 is 1, I to the 1 is I, and I to the 2 is negative 1. Therefore, if we wanted to take the square root of negative 1, it's technically the same as taking the square root of I squared. The square root of I squared is just I. So in other words, the square root of negative 1 is an imaginary number. We cannot take a square root of a negative number because 1 times 1 would give us positive 1. Negative 1 times negative 1 would also give us positive 1, but a negative times a positive, these two numbers are no longer the same. And when it comes to simplifying radicals, you have to have the exact same numbers. So that's why it's impossible to take the square root of a negative number. Negative numbers inherently have a positive and a negative. These are not the same number. That's why we have to use imaginary numbers to define them. So let's go over to another example. If 2 to the 0 equals 1, 2 to the 1 equals 2, and 2 to the 2 equals 4, then square root of negative 4. Here we're going to try and simplify this. So we know that the answer can't be 2 or negative 2 because it would take a positive and a negative number to make negative 4. These are not the same number. We need to make them the same number. The only way that we can do that is if we remove or factor out a negative 1. So what I mean by that is if we said negative 1 times 4, we could now simplify. We could also separate them to make it seem a little bit easier. I know that the square root of negative 1 is I. I know that the square root of 4 is 2. So then my ultimate answer would be I times 2 or just 2I. Let's try this with another problem. First thing we're going to do is pull out the I. I see that there's a negative. You can rewrite these steps, but you don't have to. As long as you see a negative in the radical, know that you can pull the I out immediately. So this can become 2 times I times the square root of 8. Now we've gotten rid of the negative inside by pulling out the I, and we can go to step 2, which is prime factor the radicand. So I know that we are now going to simplify. We can kill one, bring one out, and this 2 stays on the inside. So our final answer is going to be 2 times I square root 2. This 2 came from the 2 on the inside. This 2 stayed on the inside because it had no pair. 2 times 2 is 4I square root 2. Now let's use multiplication. 4 minus I quantity squared. That should say I, not 1. Please change that. We can expand this. And use foiling to simplify. 4 times 4 is 16. 4 times negative I is negative 4I. Negative I times 4 is negative 4I. And negative I times negative I is positive I squared. Now there's 2 things I can do to simplify. The first thing I'm going to do is combine my like terms. Negative 4I and negative 4I make negative 8I. I'm going to bring down my 16 and my I squared. We know that I squared is equivalent to negative 1. So I'm going to cross out I squared and replace it with negative 1. We can now combine 16 and negative 1, which will give us 15 minus 8i. This is the standard form for a complex number. It's complex because it's made of a real number, which is 15, and an imaginary number, which is negative 8i. This is the format of A plus BI, which we went over in our previous notes. A plus BI is our standard form, so you always want to put the real number first and the imaginary number second. In the next problem, we're going to add and subtract. The first thing we're going to do is distribute our negative 1. So negative 1 times 2 is negative 2, and negative 1 times 2i is negative 2i. I'm going to bring down negative 3 plus 5i. Now I'm going to combine like terms. Negative 3 minus 2 is negative 5. 5i minus 2i is positive 3i. And this is in the form of A plus BI, so this is our final answer. We cannot simplify it anymore. Remember that negative 5 is a real number, and 3i is an imaginary number, which makes a complex number. And it is complex because it is made of both imaginary and real numbers.